Hello everyone, my name is Camila Torres. I am the instructor for this course. This is CEDC 705 and CEDC 705.5, Mathematics Curriculum and Methods. In today's video, we're going to discuss how problem-solving techniques can be used and should be used to help students learn mathematics. In the last video, we discussed how we can incorporate a few of the cognitive and developmental psychology tenets into math instruction. We paid particular attention in using the concrete, representational, abstract pathway to help students acquire knowledge by using manipulatives so that they can see the mathematics themselves, they can manipulate it and engage with it. It becomes active learning. Also in the representational phase, where students are forced to make sense of the problem by themselves and assign their own representations. It also gives them time to reflect as they work with the language and they color and draw what they've learned. And then finally moving into the abstract phase, where students are seeing mathematical symbols as a manner to communicate, and that they can derive meaning from those symbols too. In today's lecture, we're going to continue looking at ways that we can help students learn mathematics and looking at another constructivist method that we can use, that we can piggyback on to have it be most meaningful for students. This involves using problem-solving techniques to help students learn math. So in 2001, right about the time where they were starting to make changes in curriculum instruction for mathematics, another report or book, I think it might have been, came out called Adding It Up, Helping Children Learn Mathematics. And in that book, which has directed a lot of the documents that we use now, they wrote, a goal of mathematics instruction is for students to become numerically powerful and proficient. According to the authors, numerically powerful and proficient students had the following components. So looking at these components that the authors argued were essential to qualify a student as numerically proficient, the first one, conceptual understanding, we've already discussed. As long as students were able to tell you what was happening in the background, the theoretical underpinnings of a topic or a subject or domain in mathematics, and they have been able to transfer this to the symbolic stage and be able to use the traditional algorithms, then it could be considered that they had both conceptual understanding and procedural fluency or proficiency. The next two we haven't really discussed, and that's what we're going to focus on this lecture, is strategic competence, the ability to formulate and represent problems, and adaptive reasoning, the capacity for logical thought, explanation, and justification. This last one, which happens to be my favorite one, we're going to hold off on for a little while. But I want to talk about these two because we have to think to ourselves, as teachers, how do we teach strategies? How do we teach students the ability to adapt to a situation and apply logic? So, how do we teach strategic competence and or adaptive reasoning? So we teach these components using problem solving, but we incorporate cognitive and development psychology theory into that. When we're looking at problem solving, there's really different kinds of problem solving teaching that you can do. We're going to look at each one individually, but there's teaching for problem solving, there's teaching about problem solving, and there's teaching through problem solving. Let's look at each one in more detail. If we were teaching for problem solving, we're teaching skills, some sort of standard, and then we're providing problems to practice those same skills. I mean, I can remember back when I was in school, elementary school, this is how we did word problems. Like the teacher would assign homework and maybe the first 20 problems would just be numbers. When you just have numbers, those are called naked number problems, where they just give you the numbers and you compute. And then the last couple problems at the end of the chapter were always the dreaded word problems. So what the teacher was doing there is she was teaching us how to do computation, and at the end, she was giving us an opportunity to use the computation in a word problem, right? You could argue it was a real life problem. So here is an example. Here I have a naked number problem that is 4 plus 7. Maybe the students got 10 of these type of problems. And then a couple of these would be a word problem. And this one, I have the last time Professor Torres checked her roster, there were 4 students, should be students, registered in her class. She received an email that 7 additional students added the course. How many students total are on Professor Torres's roster? So here we're just basically adding in both situations. But after practicing with some naked number problems, they give you something that you could argue was in context. But ultimately, you're just practicing a naked number problem in words. That's teaching for problem solving. Teaching about problem solving is teaching a process so that the students can actually apply a strategy if they have an issue with solving the problems, if they get confused. So an example might be, if you get stuck on one of the problems that I've assigned, I want you to try drawing a picture or working backwards or making a table. So the teacher is actually teaching the students how to use problem-solving techniques or strategies to develop the solution. The first person to come up with this idea was a man called by the last name of Polya, 1945, where he was actually a college professor, and he found that a lot of the students coming into colleges did not have the strategies in order to persevere in solving college mathematics coursework problems, right? Their homeworks. So he sort of came up with this steps on how to solve a problem. First, it was identify the problem, then maybe develop alternatives, then select one of the alternatives, then implement it, and then look to see if it worked. Although this looks kind of like a cycle, a lot of the times you go back and forth. Let's look at each one individually. So the first step is, did you understand the problem? Asking students, do you understand all the words in the problem? What are you asked to find or show? Can you restate the problem in your own words? I've seen teachers do this a lot. You'll see this when teachers are asking students to underline key terms. They're looking for students to make sense of the scenario so that they can begin to solve the problem. This is great. This is something that we have to teach. You cannot assume that students will automatically know how to do this on their own. Helping students unpack the process of developing meaning. Next step is devising a plan. So kind of trying to decide what is the best strategy of all the different strategies that you've learned. Which one is the best strategy for this situation? The strategies that we're going to actually look at some in a minute, you really have to think about teaching them independently. You can't just tell students, well, draw a picture and see if it works. You have to teach them how to help themselves. That's part of the teaching process. Next, you try to carry out the plan. So they've selected a strategy that they want to use, and then they see if it works. Okay? If it does not work, maybe they should choose another strategy. So while students may feel like they have to choose the correct strategy first, there's nothing wrong in, with one thing didn't work, let's try something else. That's how a lot of our jobs are done. As teachers, if students need different types of differentiation and you try one and it doesn't work, you're going to try another one. You're not going to beat yourself up for not picking the right differentiation need. So we have to kind of show our students that this is a trial and error, that we have to concentrate on the process, not so much the product. As you get to know what the strengths are of each of the strategies, and as you become more adept at using these strategies, you'll be able to select them a little bit easier. That's all it is. Then, after step that is most often forgotten is kind of going and looking back. This is more than just checking your answer. While it's important to see if your answer worked, this is also the idea of what were the benefits and what were the drawbacks to that strategy. Now, by allowing students to do something like this, again, you're giving them time for that reflection that they need in order to assimilate or accommodate these concepts. So here are some commonly used Polya strategies. Things like guess and check, look for a pattern, make a list, draw a picture. Draw a picture is really big. I like that one. Work backwards, use a model or manipulatives, try to make a table or chart. I will actually create a Google Doc and link it in the description box below, and I'll see if I can also put it on Blackboard for you, as well as sort of a Polya platter that you can use for your students to get them used to it. I want to show you a couple different ways on how you can teach problem-solving strategies. I'm going to use one type of problem that is very problematic for students around third or fourth grade. They really struggle with this type of problem. Let's look at this example on division with remainders. This is a typical problem that a lot of students struggle with. It says, Professor Lacey wants to take her 27 students on a field trip to an observatory. The school must rent vans to take the students. If the vans can hold 5 students each, how many vans will the school need to rent? Now, the most common answer for students to give is 5 remainder 2. That answer is correct if this were a naked number problem. However, in context, it is nonsensical because that would mean that the 2 students would not be able to attend the field trip. They would get left behind. Now, if we were to do this as a problem-solving type of lesson where we gave this problem to the students, right? We gave them the scenario, and then we said, we're going to learn how to do this type of problem using manipulatives. This is one way you could do it. So here is the same problem. We're going to be using manipulatives. And for this, I just tried to find something that you might find around the house or be very, very easy to obtain. I'm not a proponent of spending your own money on teaching, but I've come to learn that most teachers do this. So when I try to give you advice, I try to think of a very cheap and I try to think of items that are very easy to access. In this situation, I just came up with paper cups and paper clips. So here is the scenario again. Professor Lacey wants to take 27 students on a field trip to an observatory. The school must rent vans to take the students. If the vans can hold 5 students each, how many vans will the school need to rent? So in this case, we're using manipulatives. With manipulatives, which is a concrete representation, we need to conceptualize what each thing means. And so we would tell the students, we're going to be using paper clips to represent each student in Professor Lacey's class. So how many paper clips would we need so that we had 1 paper clip per student in the class as a representation? So the students are making sense that each paper clip would be a student. Therefore, in total, we would need 27 paper clips to represent the students in the class. Then you would tell the students, we're going to use the paper cup to represent a van. How many paper clips should go in a paper cup? And the students can say, well, if the van is a paper cup and the students are the paper clips, then we need to be able to put 5 paper clips in each one of the cups. After they've done that, they can see that they're going to have these 2 paper clips left over, and those 2 students are going to need their own van into this paper cup. And then by counting up however many paper cups there are, they would be able to answer the question. They will need 6 vans in order for everybody to travel on the field trip. So what are we doing? We're using manipulatives. We've conceptualized all the pieces of the manipulatives. The students are the paper clips. The cups are the vans. By sorting the paper clips into the cups appropriately and making sure that all the paper clips get to go into a cup, then we can just count up the cups at the end and find out how many vans will need to be rented. So this would be a concrete stage in a problem-solving task. And this is how we would use students, how to use manipulatives to perhaps work with a problem that they don't understand from the onset. Another way that you can do this is draw the picture strategy. Here is the exact same problem. This time, the students, after they've maybe worked with conceptual understanding using the concrete manipulatives first, now perhaps they can just draw the students and then group them by fives to see that they will be grouping them in terms of the van, and then the two other students at the end will also need their own van, or they won't be able to attend the field trip. In the future, you want to give students these type of practice problems. You can tell them, we're going to be doing this problem. We're going to be doing some problem solving today, boys and girls, and I would like you to apply the draw a picture strategy. I would like you to apply the use a model strategy. And then as you start to develop more types of strategies in your students, you can tell them, I would like you to choose the draw a picture strategy to solve the problem, and I want you to choose one other strategy of your choice to solve the problem. Okay? In this way, we're developing a holistic understanding, we're developing problem-solving strategies, and we're reinforcing all those educational psychology components that are so essential in student learning. So I want you to take a second and go ahead and try to use one of these problem-solving strategies, one of the Polya strategies, to try to attempt to do this riddle. The riddle is, there are 4 persons, person A, B, C, and D, who want to cross a bridge at night. Person A takes 1 minute to cross the bridge. Person B takes 2 minutes to cross the bridge. Person C takes 5 minutes to cross the bridge. Person D takes 8 minutes to cross the bridge. There is only one flashlight with them, and the bridge cannot be crossed without the flashlight. There cannot be more than 2 persons on the bridge at any time. And when 2 people cross the bridge together, they must move at the slower person's rate. Can all of them cross the bridge in 15 minutes? What I would like you to do, and there's no way I will ever know if you did this, is to go ahead and pause the video here and give yourself a moment to try to do this problem. Use one of the Polya strategies and see if you can document how you did so. Here are some of the Polya strategies for you to be able to select the one that you feel is best. If you'd like to pause the video now, you may. I'll go ahead and put a slide for the pause here. How did it go? Were you able to solve the logic puzzle? I will try to find a link with a solution and put it into next week's module. The last type of problem-solving technique is teaching through problem solving. And this is when students learn the concepts through a problem-solving lesson. So it's not direct instruction. It's the actual aha, I figured out what's happening here on my own. And the skills emerge from working out the problem. So I'm going to go ahead and use a simple concept of multiplication. And here we have a multiplication chart that goes from 1 to 12 in the columns, and then also 1 to 12 in the rows. Okay, and then the numbers are just filled in here with all the multiplication facts. And this is very typical of what you would see in probably 2nd, 3rd, and 4th grade as students are starting to become very fluent with their multiplication facts. Traditionally, they were often told to memorize the multiplication facts. I guess what we're going to discuss here is kind of looking at the background of multiplication facts and how that actually looks in space versus just memorizing. Just to establish some facts here, multiplication can be seen as repeated addition, but there's also more to that meaning. When you multiply any two numbers, you will create a two-dimensional figure or a rectangle. When you multiply any three numbers, you will create a three-dimensional figure or a prism. And these ideas of multiplying and dimensions being created based on how many numbers you're multiplying are directly linked to the understanding of algebra. So let's see what I mean by rectangles. Now here I have 1 times 1, and of course my answer is going to be 1, and I have one little square here that is symbolizing that 1, and it's an actual square. Remember that a square is a rectangle. It's a special rectangle. Let's look at the number 2. Here I have 2 times 1, so I have 2 squares right here. They form this rectangle. Let's look at 3. Here I have 1 times 3. They form this rectangle, and there are 3 squares inside that rectangle. Now let's look at 4. 4, I'm going to make this bigger. 4 appears here, where I have 1 times 4 to get 4, but it also appears here, where I have 2 times 2 to give me 1, 2, 3, 4 squares. And those 4 actually make a square. That's why 2 times 2 is 4 is called a perfect square, because it forms a perfect square. The same thing would happen with 3 times 3. Here it forms a perfect square. So this is what I mean by multiplication creating rectangles. Sometimes when you multiply, there's only one way to create a rectangle, and that might be for something like 5. The only time I'm going to see 5 appear on a multiplication chart is when I multiply 1 times 5, and I have this rectangle like this, and if I wanted to shift my multiplication chart, I could shift the orientation so that I could have the 5 sort of horizontally, or I could tilt it so that that 5 would also appear vertically. And that's actually the commutative property. One way it is 1 times 5, and the other way is 5 times 1. But the shape doesn't change. When we can only make one rectangle for that number, that's also called a prime number, versus a composite number, let's see, like the number 8. 8 can be made as 1 times 8. We get this long rectangle. Or it can also be 2 times 4, where we still have 8 squares. Dimensions of that rectangle are different. There's more than one way. One number that has lots of different ways to make it is the number 24. And 24, I could make 24 by 1 times 24, obviously, but I could also do 8 times 3. Or I could do 4 times 6. Or I could do 12 times 2. So in this type of lesson, I would give the kids cubes or square pieces of paper. And I would say, I'm going to give you a number. I want you to find all the different rectangles that you can make to create that number. So, for example, the number 5, I want you to count out 5 squares and show me how many rectangles you can make with that 5. Oh, you could only make 1? Let's jot that down. This time, let's use 8. Oh, I see that Diego has put all his squares vertically in line. And I see that Clara has put all her squares in the same way that Diego did, but she did it from side to side instead of vertically. Over here, I see that somebody else did 4 times 2. Does everybody still have 8 squares? Count to make sure that everybody has 8 squares. Yes? Show me the rectangles. Now, you did not say, okay, every time you multiply a number times itself, and that's the only way that you can make that number, that's a prime number. That's a memorization technique. This is teaching prime and composite numbers through exploration. Okay, where the idea of there's only one way to create a rectangle with certain numbers, which is when you multiply 1 times that number. Those numbers have a special name. Those numbers are called prime numbers. That's much more meaningful than just memorizing random facts. So why don't you try this yourself? So using a multiplication chart, or if you have graph paper, that's another great way to do this. Again, it gives the students time to reflect. Give them graph paper and some crayons and have them explore. Give them the numbers 1 through 24. Ask them, how many rectangles can you make for each one of those numbers? For example, the number 1 is only 1 square. You can only make 1 times 1. Only 1 rectangle can be formed. Keep track of the numbers that can be created by only using 1 rectangle only. So for example, the number 4 can be created with 2 different rectangles. The 1 times 4, or 4 times 1, which is this representation right here, or 2 times 2, which is a perfect square. So that number could not be included in your list. You could extend this to have students sort prime and composite. You could also extend this to see what numbers have the most amount of factors. This leads to a conversation about factors. Previous to this, and this is a little bit of a tangent, but it's all connected, so it's kind of hard to decide where I want to stop. But previous to this, you could also use the same idea of rectangles when you're looking at using grids to represent any sort of multiplication. By the way, when you're using grids as a representation for multiplication, this is called an area model. And what we can do using grids as a representation of an area model. So this would be, for example, using 3 times 10 plus 15. Be 3 times 10 would give you 30, and 3 times 5 would give you 15. So 30 and 15 would be 45. This is different than just showing students the algorithm of how to calculate 15 times 3. Here they're using the idea of the area model to reinforce conceptually what is being done, and it's also teaching them strategies on how they can do this type of multiplication in their head by breaking down numbers into more friendly components that they can keep track of in their mind. So this is a great place for us to stop right now. I will look forward to meeting up with you at the next lecture. Have a great rest of your day. Bye!